Hi all, welcome to the video lectures on VHDL. In this lecture, I will cover the structural modeling of a multiplier, 2-bit multiplier using the structural modeling. So before starting this VHDL coding, first we'll see the structure or the schematic of the multiplier. As I told you in the previous videos, you can make the truth table, schematic, block diagram, everything ready. As of now, as I am dealing with the structural modeling, I am just showing you the diagram of the 2-bit multiplier. So here you can see that for the realization of how the 2-bit multiplier, we require 4 AND gates and 2 half adder circuits. And the inputs will be A and B of 2-bit types, means these are bits. A0 and A1 is 1 bit and one number, and B0 and B1 is the other number. And P0 to P3 are the product terms. So to understand this circuit, initially we should go with another diagram to get the clarity on why we are using this circuit. Just observe the screen. I am taking two numbers A and B of 2 bits type. So A0 and A1, B0 and B1. So perform the multiplication the conventional way. So how we will perform the multiplication? B0 into A0. So here I am writing A0 B0, and this is multiplied here, A1 B0. Then the second one is multiplied here, and we will be writing in this place. So A0 B1, B1 A1. So these are the 4 terms we are getting whenever we are performing the multiplication. Then what we will do? We will be writing these things. A0 and B0 will be the first product, Pn of P0, and the second product will be the sum of these two. So whenever we are adding, then we will be getting the 2 outputs. One is the sum and one is the carry. So here just see this, and the sum is the XOR of the two inputs. Suppose if A and B are inputs, sum is the XOR operation of the two, and carry is the AND operation of the two. Here the inputs are A1 B0 and A0 B1. The XOR of these two is the sum, that is P1, and the carry is forwarded to the next stage. So A1 B0 and end of these two is the carry, and that is forwarded to the next step. And then now these two terms will be added. This is A let and this is B. So A XOR B will be the sum. A and B will be the carry. So this will be the product terms P0 to P3. Just minimize these and compare these two. So then you will understand the diagrams. So here you can see, the first product term P0 is the first product term P0 is the sum of there is no sum, it is simply A0 and B0, which is P0, you can see here. And the second one is A1 B0 and A0 B1. The sum is nothing but the XOR operation. A1 B0 and A0 B1 is given to the half adder, and from the half adder we will be getting the two outputs. One is the sum, that is P1, and the other is the carry, that is given as an input to the next half adder. The carry is given as an input to the next half adder. So for this second half adder, we'll be adding these two terms. That is the carry from this first half adder and the remaining term and the remaining term. So these two will be added, and the sum is P2 and the carry will be P3. So like this, we'll be defining the structure of a 2-bit multiplier. And for this structural, as I told you in the previous lectures, for realizing a logic in the data flow, the equations are important. For realization of a logic in the behavioral, truth table is important. And now for realizing a logic, for realizing a logic in a structural, components and interconnections are important. And here this is a multiplier circuit with the interconnection of the components. So from this figure what we can say, we require two types of components. One component is AND, one component is half adder. AND is used 4 times, half adder is used 2 times. Following these things, we'll be designing the multiplier in the VHDL, structural modeling. So let us go to the Vivado, double click on the Vivado icon, and let the system to respond. And in the meantime, just we'll go through the program once. See here, this is the header files, the library IEEE and std underscore logic underscore 1164 dot all will be the default libraries that will be coming whenever you are starting. So how to start this? Go to the create project. Next, I am saving in the folder demo VHDL programs, and I will select that as my destination folder. Select, and I am changing the project name as multiplier. Click on next, RTL project. Next, create a file. After confirming the target language and the simulator language, create a file type VHDL, MUL. Just I am keeping the name as MUL. Next, no constraints added here. Next, select the family as Arctic 7, package is CSG 324, speed is -1, and select the CSG 324-1. Next, and finish. So once you are finishing these things, a project window will be opened as we are discussing the program here. So initially, the two files will be by default available in the VHDL. The other two things will be the two libraries we must use. So, and also, as I told you here, this is a 2-bit multiplier circuit. So for each input A and B, we want 2 bits. So accordingly, we will be declaring the ports. You see here, a port A comma B of type vector. See here, I am declaring 2 bits, means 2 inputs A comma B of type 2 bits, means 1 to 0, means both A and B are of 2-bit types. And I am declaring a product P which is of type output. And how many bits are needed for the product? From this diagram we can see that 1 2 3 4 4 are needed. So that is why here out, that is also of type vector, and this is 3 down to 0. 3 down to 0 means 4 bits will be coming. Press OK. Then under the design sources, you'll be getting the VHDL file. So expand this, and you can see here A comma B is std underscore logic underscore vector 1 down to 0, and the P is out std underscore logic underscore vector 3 down to 0. So in the structural modeling, first we'll be declaring the components. What are the components needed here? See here, we require two types of components. One is of type AND, and the other one is the half adder. So before the architecture starts, first we'll be declaring the components. So here just I am renaming the components as AND2 and half adder 2, and I am declaring the components before the architecture begin. See here, architecture, I did not change the architecture name here. Architecture architecture name of this entity is, I am declaring one component and that component name is end underscore 2. I am declaring a second component and the component name is half underscore adder underscore 2. And one important point to be noted here is, before we begin the architecture, one more things are signals has to be declared. So what is a signal? Why we should declare? For that, again we'll go for this figure. See here, A naught, A1, B naught, B1 are the inputs, P naught to P3 are the outputs. But see, observe the cursor here, A naught, B naught is ended and we'll be getting the P naught. Observe the second AND gate, A1, B naught is ended and that is not the final output, that is given as an input to the half adder. And in this case also, A naught B1 is ended and it is given as an input to the half adder. And even here you observe one of the output of the half adder is the P1, which is the final output, but the second is the input of the next half adder. So these intermediate things will be declared as a signal. So by observing this figure, we can say that here we require one, that is S1, signal S1, signal S2, signal S3, and S4. So four type of signals are needed. So that is what we'll be declaring before the architecture. So before the start of architecture, what we'll be doing? We'll be declaring the signals. And one more important thing to be noted here is, whenever we are declaring the architecture signals, it will not be of any type, that is in or out. So it simply is, observe here, signal S1, S2, S3, S4 colon std underscore logic. We are not specifying it as in or out. Then we'll be starting the architecture. In the structural modeling, in the architecture, just we'll be doing the port mapping. I will explain you how to do this port mapping. Just type this code after the begin. After the begin means beginning of the architecture. So here what I am doing here is, A1, A2, A3, A4 are the labels for the AND gate. H1 and H2 are the labels for the half adder. So here what I am doing in the architecture, I am mapping. So what is this? Port map, end underscore 2. This is the component what we declared here, port map. So what is this end underscore 2? That is a component that will take two inputs and it will give one output. So whatever the parameters I am passing here, end underscore 2 port map, after this port map, the first two will be the inputs and the second will be the output. And see here, H1 and H2 are the labels of the half underscore adder underscore 2. What is half underscore add underscore 2? That is another component which will take two inputs and which will give two outputs. So which will take, the first two will be the inputs and the second and third and fourth will be the outputs. So here one more important thing we should observe is how we can do this port mapping, how we can write these numbers, how we can mention A naught or B naught. Again, for the clarity sake, we should go for this diagram. See, observe here, for the first AND gate, for the first AND gate, A1 is the label for the first AND gate, A and underscore 2 port map. So A naught and B naught are the inputs, A naught and B naught are the inputs, and P naught is the output, and P naught is the output. And for the second AND gate, A1, B naught are the inputs, A1, B naught are the inputs, and the intermediate signal S naught is the output, because that is not the final output. S1 is the output. For the third AND gate, A naught B1 is the inputs, A naught B1 is the inputs, and the signal S2 will be the output. Signal S2 will be the output. For the third, A1 B1 and signal S3 will be the output. So, and similarly, for the half adder also, we'll be giving the two inputs and we'll be getting the two outputs. Observe here, for this half adder, the signal coming from the second AND gate and the third AND gate. The signal coming from the second AND gate and the third AND gates are the inputs, and P1 is the first output and the signal S4 is the second output, that is the carry. So here mapping accordingly. S1, S2 will be the inputs, which are the inputs of these two AND gates, and the output will be the product 1, P1, and the carry will be given to the input of the second next adder, next half adder, that is S4. Next, for this half adder, the second component half adder, what we'll be doing, half underscore add underscore 2. The input is this signal which is coming from the first half adder, that is S4. The output, this is the output of the first half adder, that is input for the second, and S3, that is the signal coming from this AND gate. So these are the inputs, and the outputs will be P2 and P3. So after doing the port map, the programming is half done. The programming is half done. So here, whenever you are directly assigning these inputs and outputs, you'll be getting a warning. You can neglect that. So after typing these thing, the important point to be noted here is, after typing these in the architecture, press Ctrl S, save the program. After saving the program, you can see it is updated, and in the design sources, you can see that a tab is open, and click expand that. And once you are expanding that, you can see the labels of AND gates and half adders, whatever we mentioned here. And you can observe the red question mark here, which indicates the components are added, but it is of no logic and it is not in a working condition. So what is the next aim is to write the code for these components. Make a note of these, students, because after typing this program, the structural is not completed. So after typing this thing, you should save and expand here, and you should go for each component and type the logic for that. So here anyhow, if we are writing the logic for one AND gate, and that will be automatically given for all the AND gates. So now how to do that, and what are the rules to be followed? So observe the video carefully. Right click, add sources, create a design source, next, and create a file. You should be careful with this. Whenever you are creating a file, the name should be, file type is VHDL, and the file name should be same as that of the component what you declared. And underscore 2, and underscore 2. Okay. And click on finish. So once you are done with these things, my suggestion is don't give the port names here. And here I am going to write a data flow model here. That is why I'm just changing the architecture as data flow. And don't give the port names here. Just click OK. Yes. So once you are adding the component, you can observe that the AND gate components will be changed. See here, the components where the AND underscore 2 has been changed. Means we added the source, but there is no logic. Double click on any of that, go here and write the code to make sure that you are typing the proper components. See here, I came to the main program where I declared the component AND underscore 2. Copy this and go to the component and use that in this port. The name should be same. Whenever you are declaring the components, what are the inputs and outputs you are giving, the same should be mentioned here. And write the logic. Simply write a data flow model for the AND gate. Output X is assigned with A and B, semicolon. That's it. So now the AND underscore 2, the component whatever you declared, will become the AND gate, and that will be serving as an AND gate. So now what is other one remaining here? You can observe here, half underscore add underscore 2. Do the same procedure. Go to right click, add sources. Next, create a design source. Click on next. Uh, Click on create file, and file type is VHDL, and be careful, the name should be same as that of the component, half underscore adder underscore 2, and press OK. And finish, and don't add anything. Just change, if needed you can change the architecture name, or else you can just keep it just like that. And I suggest not to give the port names here. So how to give the port names? Let it update. Now the logic is added, means source code is added. Go to the main source where the half underscore add underscore 2 component is added. Copy this from here. Control C, come to this component half adder 2, paste it here so that the names will not be changed and you will not get the error in the future. See, we know that for the half adder, sum is nothing but A XOR B. That is the logic for the sum. A XOR B, and carry is nothing but the end of A and end of the inputs A and B, semicolon. So now save this, and now this will be acting as half adder component. Now this component will be working, and you can clearly see that for this structural, whatever the components we added, all the components here you can observe the color has been changed, and in that each component, if you are adding the component and 2, the logic for the component and 2, that will be working for all these and underscore 2. If you are adding for one half underscore and underscore 2, that will be working for any component, any number of components with the same name. So after doing these things, go to the main program and save it, and go for run simulation, run behavioral simulation. If any error is there, it will display. Otherwise, will be displayed with the uh, waveform window. So here you can see the waveform window, and whatever the procedure we are following for all the experiments, you can follow the same. Here you can expand this and give the inputs here for both the A, and here also you can give the inputs for the B. So here force clock, binary, leading edge is 1, trailing edge is 0, cancel after 2000 nanoseconds, and here I am just giving it as 100 nanoseconds. Right click, force clock, binary, leading edge is 1, trailing edge is 0, cancel after 2000 nanoseconds, and time period I am changing to 120, let 120 nanoseconds. Then coming for this B, right click, force clock, radix is binary, leading edge is 1, trailing edge is 0, cancel after 2000 nanoseconds, and here I am making it as 150. I am changing these time periods in the view to get all the combinations. And for this B, second part of the B, I am going with the force clock, radix is binary, leading edge is 1, trailing edge is 0, cancel after 2000 nanoseconds, and this will be a different time period of 150 nanoseconds. Click OK and execute. Once you are executing, we'll get the outputs like this. So for seeing the outputs, expand this p term also. Click on the zoom fit. You can see the waveforms, and you can zoom to the extent where you can see the outputs, and drag this. So you can see the multiplication on this values window. So 2 into 3, 6. So whenever you are moving this cursor, you can see the multiplication of A and B will be the product term P. So like this, you can see the outputs in the structural. And why the structural is important is, after this simulation, we will be going for the open elaborated design. Click on OK, and just we will see what is the output we are getting here. So in the structural, whatever the components we started with, that is this one. Whatever the components we started, and gates and the this one, and gates and the half adders, we will be getting the same here. We must get the same here. Let us check. So after this RTL analysis, we will be getting a elaborated design. In all the structural modeling, we will be getting the interconnection of components. You see here, we are just getting this, whatever we have drawn. So AND gates, half adders, AND gates, half adders, you can click here, you can expand, and you can see this half adder circuit also here, which contains that. So half adder circuit and gates, and clearly whatever the diagram we have drawn here, the same diagram will be getting here, and that is the advantage of doing the programming in structural. And then finally we'll be opening the synthesis report, and as I am telling from the previous videos, simulation and the synthesis will be same for all the modelings, only the schematic, that RTL analysis, the schematic diagram will be changing. Thank you all.